Welcome to this 10th lecture video for Physics 4A. As mentioned previously, in this set of lecture videos, we are looking at a computational tool that can be very helpful in your physics problem solving. This tool is SageMath, a free and open source software computer algebra system. We will start with a mini tutorial that covers most of the basics and can get you started using SageMath right away through the SageMath Cell website. Then, I have some excerpts from my problem-solving videos demonstrating the use of SageMath in the context of these homework problems. Each of these problem-solving approaches are divided into two parts. In the first part, we use our knowledge of physics to come up with a system of equations. And in the second part is just math. The video excerpts show this second part. In the first example, you will see the calculus functionality of SageMath, taking derivatives and calculating integrals. The second example is the typical use of SageMath in this class, solving a system of equations similar to the example you saw in the mini tutorial. In the third example, you see me handle a bit of complication involving trig functions in trying to solve for the angle theta. SageMath is great at handling polynomial equations, but when it comes to special functions like trigonometric functions, some care is needed to use it effectively. The examples 4 through 6 are from chapters we have not yet covered, but our approach to the math part of the problem solving remains the same. And you can see the great simplification and time saving we can get from a computer algebra system like SageMath. In addition to using it in problem solving examples throughout this class, we will bring SageMath back for another lecture in the second half of the semester for help with solving the ordinary differential equations we encounter in analyzing simple harmonic oscillators, i.e. mass on a spring. SageMath is like a calculator for algebra, and it can reduce a lot of frustration. And I think I should have a more proper instruction for teaching you how to use that tool. I rewrote this lab a year ago, specifically to kind of have a portion of it that guides you through use of SageMath. So let me work through this part of the lab and maybe explain some things as we go. And I hope that'll serve as a bit of an introduction to SageMath, and so that you can use it for yourself, either if you're following along in homework help videos where I use it, or some homework help videos I do the algebra by hand, but maybe you've done enough algebra by hand and you just want to use the calculator for symbolic algebra. Okay, so with those preliminaries, let me just read through this lab manual. And even though this covers the topics that we haven't covered in class yet, for the purpose of covering use of SageMath, it doesn't matter. And in fact, this is how I recommend that you approach any physics problem. Always think of separating into two parts. The first part contains all the physics. That's the part where you use your physics knowledge to set up your system of equations. That's the physics part. And once you have that, then for the second part, it kind of doesn't matter whether you know the physics or not. Once you have the system of equations, then you're just doing math to solve through that system of equations. So what we are doing here is going to be basically the second part. Somehow somebody has set up that system of equations for us, and we are just gonna use SageMath to solve the system of equations that someone has set up for us. So let me start reading through the lab manual. In this class and elsewhere, you have seen me use computer algebra system, CAS or CAS, either to demonstrate use of computer algebra system or to use it as a shortcut for complicated, tedious steps of algebra. For avoidance of that, you can get through this whole class, including this lab, without using a CAS. However, I strongly recommend that you go through below exercises now, learning a small amount of CAS usage, so that when you see that you have a complicated system of equations, which will be the next part in this lab, you can either use the CAS to solve it or use the CAS to double check the answer you obtain by hand. The CAS I use for this class is SageMath. If you have it installed on your device, you can use it without access to the internet. If you don't have it installed on your device, the quickest and easiest way to get access to SageMath on the internet is through the SageCell website, which I have loaded on the right-hand side here. The instructions here will assume that you are using SageCell website. Some steps might need to be slightly modified if you are using interactive command line version of SageMath. SageMath has a built-in documentation system that can be accessed through help command. We are going to be using a command called var for variables and a command called solve to solve a simple system of equations. Go to SageCell website and run below commands one at a time to take a brief look at the documentation first. So with the help command. So with the SageMath, if you know any Python, you can use your Python knowledge in SageMath context because SageMath is built on Python. A lot of Python commands will just work in SageMath. So the documentation system that it has, that is the Python documentation. So like a help function that's, I don't know what it'll do if I do this. Oh yeah, if I just run it like this, then it does the things that Python's the documentation system will do. And you can do this, type Python help, you can do that. Evaluate and yeah. Now you can't do interactive stuff. That's where this error is popping up. This is one limitation of the SageMath cell, that you give up the interactivity of the normal Python scripting interface. So, but if you have a SageMath installed on your computer, you can use it interactively as well. So there's the var command that, let's say you don't know how to use it and you get these errors and whatnot. Then if you do help var as it is in this help line here, or the command example there, if you run that, click evaluate, then you'll get the built-in documentation for the var function. The documentation has two parts. The first part describes the function. It describes what kind of inputs it takes, any notes, what output you get. And this part can be fairly dense to get through, especially for people who might not have that much experience in programming. You're not used to reading programming documentation. So oftentimes the more useful part of the built-in documentation is examples, because with the examples, you can just kind of see how is it being used. Sage command, that's how they are entering the vars. So somehow they are trying to define 3 variables, and you can separate them either with the spaces or with the commas, or you can define them. They are showing all the different ways you can do. Find the one you like and do that. I think I like this syntax the best. So yeah, that's how. When you look at this built-in documentation, I recommend that you look through the examples, because those are going to be a quick way of saying how do you use this. So that's what the lab manual instructed us to do. Type above line. Okay, so type in above line in the input box below the text, type some Sage code below and press evaluate. I've done that. And click on evaluate. For the rest of this lab manual, whenever you see a block of indented monospaced text as above, it is intended as a block of code that can be entered into SageCell website. Read through the output, which is the built-in SageMath this output. For the var command, pay particular attention to example section. That's what I'm saying. Other parts of documentation can sometimes be too dense to understand at the first reading. When you feel comfortable with the var command, run below line to look at the documentation for the solve command. That's what we'll be using to solve through a system of equations. So help solve. And again, this is the built-in documentation. And again, there's this example. And I will follow through this example, even though I do it slightly differently. But hey, let's just use this as a starting place. And if we want to change anything, we can change your stuff. They also have documentation for the help command itself. If you feel like it, try running help. I think I kind of did it, so I won't do it again. So let's consider working out the problem done in below video for OpenStax University Physics Volume 1, Chapter 12, Problem 35. So for our purposes, whatever the physics context is, doesn't matter. That's part 1 of working through a physics problem. We are just skipping to part 2, where we have the system of equations, and we are just solving for it. We have a system of 3 equations, and now we'll solve for it. So at the 9-minute mark in the video, we have a system of 3 equations, which I'm not going to say out loud because that'll take long. And although in the video we work through the algebra by hand for some additional time, it's at this step we can work out the remainder of the problem with the SageMath instead. We have 3 equations and 3 unknowns, left tension, right tension, and mass of B, m subscript B. We can define a system of equations in SageMath and use solve function to solve for these 3 unknowns. I'll explain part by part the next set of SageMath code I want you to type into Sage style website. If you want, you can type in or copy and paste the whole block at the end, but so that you understand what the code does, I'll explain it after each part below. So, and by the way, you can gain some level of interactivity by just clicking evaluate after each line. So there's this first line where we are defining all the variables. So TL, TR, M1, G, M2, MB, L, and because I have a couple different things named L, so for the next 2 things I'm just going to spell out L2, L3. And so if you just run this one line, what SageMath will do is it'll declare these variable names as symbols that might potentially get used in a equation context. And for the example of the solve command you saw before, you see it do something like this, like assign all these into the it's a Python or SageMath variables. Okay, you can do that. I'm not quite sure what the function of that is because I guess in the SageMath cell, that hides the output. Okay, so I like to keep my codes simple, so that's why you will see me not really do that assignment thing. Because with this variable command, you've declared the symbols you need. So I'm gonna keep it simple. Just do it this way. You have to declare all the symbols you are going to use in your expressions. SageMath has X symbol built in. That's the one symbol you don't have to actually declare. But all other letters or symbols need to be declared. I usually use my variable names with the subscripts ignored. That is, I define M1, not M_1. Although both are valid SageMath variable names. Note that your symbol cannot start with a number. M1 is a valid symbol name, 1M is not. And there are a few special keywords that you should be aware of and avoid using as names. Lambda, all lowercase, it's a special Python keyword that you can't overwrite at all. If you try, you'll get an error. N, the function n is used to get decimal approximation of an exact expression. I recommend not overriding it so that you have access to it. And the usual suspects of numerical constants, such as E for Euler's number and pi for pi. If you accidentally override useful function or numerical constant, you can undeclare symbols by using the reset function. So here, for example, with the variables declared, if I type in TL, it'll show, TL, it recognizes it as declared symbol. But if I reset it before I do that, then it'll error out because I reset it here, so it doesn't know what TL is. Okay, so now in the next 3 lines, I'm going to be defining the 3 equations. So, well, I'll stay here. The equations are up above in the lab manual in the human readable format, but this is fairly readable, so I'll just type it in. So, so I like to put each equation into its own SageMath variable so that I can refer to them succinctly later. So that's what I'm doing here. So equation 1 is that SageMath variable is being assigned this expression, which is going to be an equation. TL plus TR minus M1 times asterisk G. Now in SageMath, you have to be careful to always indicate multiplication because the way it was written above in a human readable format, we had implied multiplication, and SageMath doesn't understand that. So you have to make sure you always put in multiplication symbols. Minus M2 times G minus MB times G is equal to the 2 equal signs. It has a different meaning from a single equal sign. This in programming language, what's called, it's an assignment symbol. It assigns what's on the right-hand side as a value for what's on the left-hand side. What I have here is a logical operator. It's an equality. It tests if what's on the left-hand side is equal to what's on the right-hand side. Now, in this symbolic expression, it's just a part of the equation. So that left-hand side is equal to 0. That's equation 1. Let me type in equations 2 and 3. Equation 2 is 0 plus L times TR minus L divided by 2 times M1 times G minus L spelled out 2, that's part of the variable name, times M2 times G minus L spelled out 3, part of the variable name, times MB times G is equal to 0. Again, for the time being, I'm not really thinking about if these equations are right, and just typing in a system of equations that someone has developed for me. Equation 3 is going to be assigned TL equal to 2 times TR. Now, if I click evaluate here, it won't actually print anything because with this being assigned to these variables, the SageMath cells default behaviors not to put any output. If you want to check what equations 1, 2, and 3 look like, I can print it like this. So what is here? So Python has hence SageMath has 2 different kinds of lists. This is what's called a tuple. And if I do this, it'll just print that tuple like this. And if I do this with the square brackets, what this is it's something called a list. And for our purposes, I guess I'll say there's no big difference between tuple and a list. I like using tuples for a simpler list of things because it is a simpler object. A list is actually a more involved object, but for the way we are going to use it, doesn't really matter. So don't let either the difference between parentheses and square brackets confuse you. So now here I can see from printing this out that equation 1 is correctly defined as I typed in there. You might see some things reordered. That's totally fine. SageMath does its own bit of a simplification. But what I'm seeing is that what I see printed here is equivalent to the equations I've typed in. Okay, moving on. Above commands define variables equation 1, equation 2, and equation 3 in terms of symbols we declared. Note, all multiplication has to be shown explicitly. Yeah, that's what I was describing earlier. And 2, equal sign is an assignment operation. It assigns what is on the right-hand side of that into the SageMath variable that is on the left. And the 2 equal signs is an equality symbol. This distinction especially matters when you're assigning an equation into a variable. If you want to check that the variables are correctly defined, you can check it using print command. Yeah, so one other way to do that is I can do print, just explicitly tell SageMath to print these expressions. Then it'll print these equations one at a time. That's another way to display these equations for double checking. Okay, with the equations now defined, we are ready to use the solve function. Below is the command that will solve for TL, TR, and B, treating all other symbols as known. So solve, and I guess there I use the list version of it. Let's just use that. List of equation 1, equation 2, equation 3. That's my system of equations. And I tell it to solve for following variables in order. So TL first, and then TR, and then MB. And let me read the rest. The first argument to solve function is the system of equations. The square brackets enclose element of a list, list the Python object. Again, if you use parentheses, it'll be a tuple. And for our purposes here, they are functionally equivalent. The next set of arguments are the unknowns to solve for. Number of unknowns have to exactly match the number of equations, TL, TR, and MB. The output of above command should look like a list of lists, and I'll explain that. And so specifying these to be solved for also kind of tells SageMath that all the other symbols that might be in the equations, that they are known. They are something that you can plug in numbers of. So when I click evaluate here, what it's going to do is it does this solve thing, and what it has solved there, it's a list of lists. Wonder if I do print, if it'll print a little bit more prettily. It might not. Okay, it didn't. Yeah, I mean a little bit, but it didn't really help. So okay, the output of above command should look like a list of lists. So this is what it means. So you can see the list here. That's a list, okay, outside the list, and it contains as its element another list. So that's what it means. It's a list of lists. So I will explain the meaning of the output below the block of command you can now run to obtain. Run the below block of commands. Everything after hashtag or pound sign is a comment, which means it is added on as an explanation for humans looking at the code. SageMath/Python will ignore it as it runs the code. So, so that's the comments that I was going above here. And the difference between using SageMath cell and the interactive version is in the interactive version, if you typed in one line at a time, you can then run this final line and it'll work. In SageMath cell, basically everything that this will depend on have to be all here. So if you're doing one line at a time, you have to do it by just adding on the lines. You can't get rid of previous lines. So let me go back to not printing this. Then the output looks like this. If you do the word wrap here, I have to kind of scroll to the right. So the output should look like below. It's a little long. It's a list of lists, meaning the outermost is the first list. It contains as its element other list. That is the next inner list. Because we had a linear system of equations, that is first order, no squares, no cubes, no fourth power. The system of equations had only one solution. There are times when there will be more than one set of solutions, like if you are using SageMath to solve through a quadratic equation. So the outermost list contains only one element. The next inner contains three elements for solutions to TL, TR, and MB. Our three unknowns. It's a little more manageable working with these returns if we put the result into a variable and look at one element at a time. Replace the last line of the block of code with an assignment into a variable, solution sol equal to that. So that, and you see that this bit has been added. Do I ever explain it? Let's see. So that sol is our variable containing our system of solutions. We can add lines print sol 0, print sol 1, and print sol 2 so that we can look at one solution per line. With these changes, the block of code looks like, and yes, you have to run the, oh, I guess I never explained this. So this is the SageMath, or again, Python syntax for referring to each element of a list. So solve had a list of lists. So I want to get the first list in that outer list, or the zeroth element. That's the first. So I want to get this out of solve. That's why I added this little bit, addressing that index 0. That's going to just get that first element out of the outer list. So I have solve there. And if I evaluate here, it'll be just a blank. That's why the instructions have you to print this. So if I do print solve, what you will see is the just that list. That is your actual system of solutions. It's a little hard to look at. So now what I'm going to do is get it one element at a time. First element, the second element, and so on. So I'll print the first element of the solve variable, and then the second element of solve variable, and the third element of solve variable by doing print, parenthesis, solve, square bracket, 2. And here the square bracket actually matters. You can't do it as parenthesis, it'll give you an error. Okay, I evaluate, and now you see the 3 solutions are put this way. So now the final step in this, let's see. Yeah, I think we can add a line so that we can with these changes, the block of code looks like, and yes, you have to run the whole block all over again. This is one of the limitations of the SageCell website. Now the final step of this brief introduction to CAS with the example of SageMath. Suppose you want to find the numerical value of MB, as in the homework question that we are working through. You don't really want to do this by hand. 1, it's tedious. 2, you might make a calculator mistakes. I make a calculator mistakes as the expressions are complicated. A CAS like SageMath can also automate the step of plugging in numerical values for symbols in a syntax called substitution. In SageMath expressions, this is implemented with the bound method, by which we mean a function that is bound to an object. Python is an object-oriented programming language. So bound method, subs for substitution. Bound method in Python is used by appending a period, subs, to the expression that the function is bound to. For example, to plug in values, these parameters, the values in the video so that you can compare them with the manually obtained value. Into the solution for MB, you call the bound method with the following command. So you have a reference to the object, sol2, that's gonna basically refer to this expression that we are printing just before. And that expression will have a bound method, subs. Now you can actually bring up, so if you don't know the syntax already, then what you can do is you can bring up the built-in documentation for that bound method. So when I do that, this is what you see. So it'll first print these 3 lines as before, and then it shows help on built-in function substitute method, which is bound to that. It shows all these examples. What the examples are showing in this verse expression, substitute with the, and it shows a few different ways you can specify the values. I like the keyword arguments because those look natural, but there might be contexts where a dictionary argument might work better, or relational expressions might work better. This actually allows you to use one of the solutions as an input to substitute, or you might want to do other stuff. You can do a list of lists. So anyways, so this is something you can read on your own later. I'm going to use the substitute function to plug in numbers. So let me plug in, I'll just follow this command. You call the bound method with the following command. I already typed this in, and I'm saying m1 is equal to m. So I guess it's I'll say equal to, but it's the keyword argument. So the keyword m1 has the value on the right hand side. So that's what that keyword argument in Python context is that M2 is equal to 58, L is equal to 7.0, L spelled out 2 is equal to 1.0, L spelled out 3, part of the variable name, is equal to 1.5. So keep all your numbers in basic SI units, and the meaning of the numerical output will be clear. It'll be in basic SI units. Updating our previous block of code with this new line and print it for display. We should have, by the way, I don't think we need that print thing. As long as I'm just looking at this, I can just evaluate and it'll still print the last line. Yeah, it still prints the last line. Different ways to do it. Then with that, it says MB is equal to 6, I assume kilograms. And to check if it's correct, you can go back up in the video and check. And these are the two main ways that I use SageMath in this class. I use it to solve a system of equations, that's the solve function. And I use it to help specify values that I use for calculating numerical value in a kind of logical fashion. That's the substitute function. And those to automate some of the tedious tasks and kind of makes it clearer that whether I made a mistake or not. If I plug it in M1 equals 40 instead of 50 by mistake, if you see me plug it into this expression, it might be hard to notice it after, L times M1 was 40 instead of 50. But in this syntax, you can clearly see, oh yeah, that was supposed to be 50, not 40. So yeah, that's the brief introduction to CAS, to the point where you can use it for some of the analysis in this lab. Again, it's not required that you use CAS, but as a calculator for symbolic expressions, a CAS like a SageMath can reduce points of frustration in dealing with complicated algebra, which is really unproductive given that this is a physics class, not an algebra class. You already took college algebra to get here. So yeah, and the rest of the lab, we don't need it. Now, later on in the semester, you will also see me use SageMath to solve some differential equations and other things. So there are other videos for that. And again, because SageMath is built on Python, it has a full like a Python syntax available. You can do things like something like this: I squared for I in range 0 to 10. So this is a Python syntax for building a list of things where it'll basically print squares from 0 squared all the way to 9 squared. So if you happen to know Python, you can totally just use it. Because SageMath will accept Python syntax. On the other hand, if you're not familiar with the programming, then you don't have to worry about any of that. So this is basically instruction step by step. We are not using any conditionals or loops. Those are more programming kind of syntax stuff. All of that, you don't really need to use it. You can use SageMath cell basically like a calculator for sometimes just numbers, 1.5 times 3.4. You can do that. You can use it as a really overqualified calculator. Or you can use it as a calculator for symbolic algebra, which is what these are. So, wow, that mini tutorial took kind of long. But I hope this is useful for those of you both following through homework help videos and maybe, in your own solution steps came up with a system of equations and now you need to do it, do the algebra. And now, one last word of caution or note. So SageMath is really good at doing calculations like this. Calculations involving linear system of equations. It's really good. It's also good at doing like algebraic system of equations. Like if it has squares, cubes, fourth power, it's really good at doing that. What it is not good at dealing with is dealing with the transcendental functions or special functions like trig functions. If you have any system of equations where it has to solve for some variable that's wrapped inside a trig function, there's a chance that it can't do that correctly. Those you might still need to do by hand. But fortunately, those kind of calculations are kind of few and far between. So for vast majority of algebra you need to do in this class, SageMath will work really well. because it's where it excels. So with that, I wanted to point out to one thing, which is that somehow if you're interested in learning more about SageMath, there's a whole tutorial that you can follow through. It claims that you can complete this tutorial in 3 hours or so. I'm not sure if I believe that, but you know, this tutorial will cover more of the detailed things in SageMath, possibly even some of the programming aspects of SageMath. So if you want to spend more time, I encourage you to do that. If, for the purpose of what I use it for in this class, this little block of text, not that block, well, the one block that I erased. Let me just go back to that. This little block of text exemplifies basically everything I use SageMath for in this class, basically as a calculator that does both algebraic calculation and numerical calculation. And these expressions are definitions. They are always true. There are no exceptions when they are not true. Whether you have constant acceleration or not, always true. Now, if you don't have constant acceleration, sometimes it might be a kind of difficult to work out the mathematics, but that doesn't make the relationship itself untrue. So with that in mind, it looks like basically what I have to do is I have to take a derivative for acceleration and take the integral here. And let me do that with the SageMath, because I mean, I can do it by hand, but let me just demonstrate how SageMath works. So I'm gonna declare some variables I'll be using, A, B, T, and I think I'm going to be defining velocity slightly differently. So my velocity, oops, that's wrong. Needed the quotation to properly define those. So for my velocity, let me say that's going to be a function of time, and it'll be function of t. I think that's right. Okay, good. Yeah, velocity is defined as function. Oh, actually, I shouldn't have done that. Okay, I'm gonna be overriding that. So velocity, my velocity as a function of time will be a plus b divided by t. And when I bring up v, yeah, it's a function, and this is the form of the function. And I need the explicit form because I'm gonna be taking the derivative. So if I take the derivative, and by the way, if you are not sure how to use a particular function, if you are not sure, so you could also Google search, SageMath differentiation. It has built-in documentation, like a help on function diff or derivative. Some functions have multiple names, and this is the built-in documentation. And some of the most useful thing about the built-in documentation is it shows you examples of how to use it. So if you're new to a particular function, it can be helpful to kind of see what are some of the typical scenarios that you use, what are some of the commands you have to put in beforehand, and that sort of thing. So I'm going to say take the derivative of velocity with respect to t. That should give me acceleration. Oh, so it gives me an expression. Now, you can't put in minus b divided by t squared. Like if you try to put that in, it'll error out. It'll say, oh, that's not right. So you have to plug in the values. And one of the things I like about SageMath is it actually lets you plug in those values. So I can take this expression. I hope I can just plug in numbers. There's something called a substitute, whose syntax I'm going to use. Again, you can use internal documentation to look up how to use that. I'm going to use the version where you use the assignment symbol to indicate the values. So I'm going to substitute things in here so I need to put in b and t. So I'll say b is equal to 0.2 meters and t is equal to, I want it at time equals 2 seconds, so 2. So yeah, there. Ignore that. This is giving me that value of that differentiation function. So minus 0.05 in the correct units should be the correct answer. Let's see. Let's test that, and then I can then get, so to get the other answer, this is one of the things I like about using SageMath. You can just change one number here. You can just use the same expression. I had the value at time equals 2, and now I want time equals at 5 seconds. It says 0.00, that's an 8. Almost missed it. Minus 0.008. So, good. I have acceleration. Derivatives are easier, so this is good. Position, it'll be a little bit harder, so let me think this through. So I have this function, and I need to integrate it. And there's a function called integrate, and there's an internal documentation on it. Now, I wonder if I can do an integral. Okay, I can do a definite integral. So I can do a definite integral from a number, time equals 0, to oh wait, sorry, almost did it wrong. So I start with x equals 0 at time equals 1. So I have to remember that. So I'm going to start with the x from 1 to, whatever these times are. And do I need to give? And I think because then the value I'm getting is the difference in position, and I'm starting at position equals 0, I can just submit that difference in position as the actual final position. Yeah, so let me do it that way. So I'm going to be integrating the v function with respect to t, and I'm integrating from t equals 1 to, for the first answer, 2 seconds. Good. Right. So that's the analytical expression with the b and a being kept as their the symbols, but I can substitute a as 2.2, b as 0.2. By the way, what I'm doing right now, it's a super inefficient because I'm having to resolve integrate every time, but it's not that complicated an expression, so I think that little bit of inefficiency is fine. And this last function that I'm using, it's giving me a decimal approximation, so that I can enter my answer as decimal approximation instead of having to, this number I want to change to 5, instead of having to put in the log and whatever into calculator. 9.123. That's one more significant figure than necessary, but the system doesn't really punish you for having extra significant figures. So when I'm not paying too much attention to sig figs, I just put them all in. Well, not all in, just round it at some reasonable place. So that's this question where it's a still simple kinematic scenario, but you have to use your knowledge of calculus and either do the calculus steps by hand or know how to use a computer algebra system like SageMath. It's a computer algebra system, but they also do calculus. It's just called the computer algebra system. Okay, the last question in this set, it's this question that I want you to do. It says, I think I can reuse some of what I had, because it's giving me the acceleration of the object. So instead of knowing the velocity, I'm given even constant acceleration, I think. It's in units of centimeter per second square, but I think if we keep everything in centimeter and seconds, it will be fine. And they've given us velocity at a particular time, and it says determine the object velocities at t equals 1 second and t equals 6 seconds. Okay. So, there's actually a pretty easy way to do this because you have constant acceleration. So you could use one of the kinematics formulas that says velocity at some time is initial velocity plus acceleration times time. You can totally use that. But let me demonstrate that these expressions are universally valid by using what I had for previous question, and I'll just, substitute in some things. So I need to define my acceleration as a function of time. It's going to be equal to 1.2 plus 1.2. I mean, constant function of time is still a function of time. So let me integrate this function of time with respect to time. And time is going to be going from, so I can use actually 4 seconds as my initial time. Nothing prevents me from doing that. the time can even go backward. Like nothing says t final has to be greater than t initial. So I can go from 4 seconds to 1 second. Now, it does result in some signs flipping, and you have to be careful. But I think when you use formalistic approach, it'll just work out. So when I do this integral, it gives me the difference in velocity. So I really have to add the initial velocity to get the final velocity. So I have to add my initial velocity at t equals 4 seconds. And it's still initial, even when I'm going backward in time. Minus 3.4 centimeter per second. Yeah. Okay, so let me check that this will give me an expression. That doesn't depend on time at all. Yeah, I guess that's right. Yeah, let me just try plugging this in, make sure it works. Yeah, and for time equals 6 seconds, just replace that 1 with a 6, and it should still work. Minus 1 centimeters per second. Yeah, I guess that's right. So the whole thing is moving to left the whole time, I think. Yeah. Long enough duration of time, it'll start moving to right, but for now it's moving to left. Yeah. So I got two equations, two unknowns, so I should be able to solve for it. Now, in a lot of the questions from this point on, I would have done this by hand, and I can also still do by hand. But since you have so many examples of these questions where I'm solving the question by hand, let me show you an example of using computer algebra system. And two equations, it's probably not complicated enough where, like using, it's like it's overkill. I don't really have to use computer algebra system to do this question, but let me just show it as a demo, just so that people can see that if you feel not quite fully comfortable with algebra, you don't have to let that be something that holds you back. There's a tool like a calculator that lets you work through algebra like using calculator. This is calculator for symbolic algebra. So when you're using SageMath, so the main thing that main function that you have to know, you might use a documentation or some way to look it up, help. The function that you need to know how to use is a function called solve. It's a function that will let you solve for a system of equations. And it's particularly powerful in dealing with the system of linear equations like what we have. So, this documentation gives you examples and whatnot. So let me follow some of those examples. So I need to define the variables I will be using. T1, T2, theta 1, theta 2, I don't need the small mass m. I'm gonna write down the version of equations where I've canceled them out. I do need a big mass m, and I do need a g. Okay, and in the documentation they have you assign these into those. I found that you don't need to. Just this declaration defines those variables, and they are ready for use. Let me write down my first equation that's based on the x direction, equation 1. That's going to be, so this is an assignment symbol, and the equation will be 0 is equal to, this is the equal to symbol, t2 times cosine of theta 2. SageMath knows these special functions, and yeah, and there's documentation that you can look up to figure out which functions it already knows and whatnot. Minus t1 times the sine of theta 1. Okay, and I'm going to write down a version of the equation where I've already multiplied it through by m, so I'm not going to write m at all. So when I do this, okay, it doesn't complain, so I'm going to assume it's right. Equation 2 is equal to 0, or equation 2 should be assigned as 0, being equal to t1 times cosine of theta 1 plus t2 times sine of theta 2 minus m capital M times g. Okay, and I entered it. By the way, so I use the shortcuts when I enter this. So here I use the shortcut for I think it's under cell a shift to enter, run cells and select below. So if you are using SageMath, like this exact setup that I have, and like when you press enter, it does this instead of what it did for me. Then it's because I'm using shortcuts. Let me know if any of that is confusing you. Um, so let's just verify that we have those two equations defined correctly. So I'm just doing this to print them. Yeah, those are my two equations. They look right. I have that minus sign there. Okay. So with the solve, this is, you can see the syntax in the example here. It's a solve and then the system of equations and then the variables to solve for. And yeah. And when you do that, SageMath will assume that all the other variables are known quantities. So I'm gonna have this system of equations, and then I'm gonna solve for T1 and T2. And it'll assume theta 1, theta 2, M and G, all those are known. So it'll do that in a bit. There it is. That's my solution. Let me put that into a variable called the source. And I can see that it's given me a nested array. That's mainly so that sometimes there's more than one solution. So that's why it's doing that nested thing. I'm just going to get the first element. So solutions is previous output. Or yeah, let me just use that. And then the first element, and then I think then it's just an array of two elements here. So let's see. Yeah, good. So if I look at the first element of this array, that's my solution for T1. So the question, so let me do it this way. I think I can just plug in the numbers using SageMath. I have all the numbers here. I can just plug in the numbers that way. So solves. I'm going to use something called the substitution syntax. So we are substituting T1, not T1, M is equal to uh, 56 kilograms and G is equal to 9.8 meter per second squared. I'm just going to make sure I plug everything in basic SI units so that my answer will be in basic SI units. I need theta 1. Now, SageMath only understands radians, not degrees. So I need to enter theta 1 as 15 degrees and then convert it to radians, pi over 180. And then and let me actually make sure this is in a decimal approximation. Theta 2 is 10 degrees, so 10 times pi over 180, so that it'll be in radians when it calculate. Okay, I think that's all the numbers I need. Let's see if it gives me, yeah, a numerical value, 542.5. And let me do the same thing for, so this is not time, it's the second element, which is T2. And I already have all the parameters values here, so just shift enter. And that's my value of tension 2. 142.6. So let's try that and see if see if it works. 542.5 and 142.6, and it agrees on 1% tolerance. So I didn't actually need that fourth digit. Three significant figures should be enough. So yeah, that's the correct answer. So yeah, as I was saying at the beginning, it is a substantial question. You do have to go through this standard strategy, and it does take some time. So make sure that you spend the necessary time. And in terms of doing the algebra, if solving for system of equations trips you up, feel free to use SageMath. Use of SageMath, like use of calculator, is allowed in every single circumstance. Data must be unknown. So two equations, three unknowns. All right. It's not solvable yet. I need to find the additional equations that I can write down. And here, I have a piece of information that I haven't used. So that should guide your thinking on, what equation should I have written down? And you have the speed of the cars moving. And you know that this is a centripetal acceleration. So you know that there's a formula from chapter 4 that relates that acceleration to the speed. V naught squared over r, and we are given the radius of curvature. So this must be our third equation that will allow us to solve for three unknowns using the three equations. So let me use SageMath to work through the algebra, and I'm seeing this non-SI basic unit, so I'll get the algebraic expression from the SageMath and then do the rest in Wolfram Alpha. Or you can also do just unit conversion in Wolfram Alpha. That's fine too. I'm just choosing to do it one way. Okay, let me first declare the variables I'm gonna use. It will be AC, normal force, theta, M. Is there G? Hey, there's no G. Oh no, there is G. Yeah, there's G. And V naught and wait, not capital. And R. I think that's all the symbols. Again, if I forgot something, SageMath will complain. So AC is equal to N times sine theta divided by M. Equation 2 is 0 is equal to N times cosine theta minus M times G divided by mass. Or let me write down the let me leave it here. I think it's going to be fine. Equation 3 is equal to centripetal acceleration is equal to V naught squared divided by R. And let me print those equations to make sure I didn't make any typos. Equation 1, 2, and 3. Okay, let me use the solve function. If you are not sure how the syntax of the function, use the internal documentation that you can access with the help. And the three unknowns are the acceleration, normal force, and theta. And let me put theta first so that it'll be the first element it'll give me. And I'm gonna put this into a variable. Well, let's see how well it does. SageMath tends not to deal well with trig functions. We'll see how well it does. If it's having issues, then I'll do some workarounds. SageMath is really great for solving linear system of equations that are algebraic. It doesn't do inverse trig functions well. So yeah, so it didn't solve anything, I think. Yeah. Oh, how do I want to do it? I think the way to do it is to turn this into a system of 4 equations. To give you some details of that trig structure. So I'll tell it. Okay, solve for sine theta and cosine theta. And in fact, so sine theta and cosine theta will be other symbols. At this point, I'm probably doing more work to get SageMath to do this than I should. So by treating sine theta and cosine theta as a separate set of unknowns, I have introducing an additional unknown. So I should give it an additional equation that will constrain them. Sine theta squared plus cosine theta squared is equal to 1. That'll, I think, give it enough structure to be able to do this algebraically. So equation 4, and I'm having it solve for sine theta and cosine theta. And really all I need is sine theta. Once I have sine theta, then I can do arc sine in the in Wolfram Alpha to do it. And yeah, and this is, by the way, if you're doing this by hand, the best way to do it would be to figure out the tangent theta, which actually I think I can. Let me do it this way. So I'm gonna do, does it have, so it has 2 set of solutions. It's understandably because of this squared thing. And Does it have only two? I thought it might have even more than two. So I don't quite care. Let's see. So this is gonna be negative, negative. Yeah, let me find use the version where actually it doesn't matter. So let me use the first element. So what I can do is I can have an expression sine theta over cosine theta, which will be tangent theta, and I can use a substitution syntax within here. So substitute. Let's see. If I do solution, first element, will this work? Oh yeah, it works. Okay, great, great, great. So what it has done, when I take the first element of the solution, it's this list of equalities. And this is actually one of the allowed syntax for substitution. Provide a list that states all the equalities that gives what it'll be substituting. So with that, it substitutes in these expressions for sine theta and cosine theta, and then it does this division, which gives that answer. So I'm just going to use this answer to use Wolfram alpha for the remainder. I don't know. You might have done it correctly, but that. All right, 0.223. That's angle in radians. So I'll just do conversion manually. 180 degrees divided by pi. I guess it doesn't understand what I mean by n. Okay, so this should be angle in degrees, 12.8 degrees. That feels pretty steep for a banking over a roadway, I think. But 95 kilometers per hour is also pretty fast speed. So yeah, that's this question. Again, if you use a standard strategy, pretty straightforward. And if you are going to use SageMath, you do I think this is right on the borderline where it might actually be less work to just you do it by hand. But if you do use SageMath, trig functions are the Achilles heel of the computer algebra system. So Mathematica does deal with it pretty well, but the maxima, which is the symbolic algebra system that SageMath uses, doesn't deal with the trig simplification all that well. So you either provided a little bit of help, giving it trig relationships in an algebraic form, or you do it by hand. Really, you should get algebra practice so that you can do these kind of things by hand. I have a sense, just an intuitive sense, that this relationship might be true. That this 1/2 k delta x squared spring potential energy, I have a sense that that might be much greater than the magnitude of this gravitational potential energy change due to the compression. If this is true, then what I can do is I can approximate this left-hand side with the expression 1/2 k delta x squared and say that's equal to mgh. And I can solve for this delta x squared without using any quadratic formula. It's so simple, I can even just do it in my head. It's delta x is equal to square root of 2 times mgh divided by k. So I am using an approximation. So as I use this approximation, I am first going to plug in the numbers and see what my approximate answer is using this approximation method. And there are some things I can watch out for to see if it's a good approximation or not. If it turns out to be a good approximation, I'll just plug in the number, see if it gets graded as correct. Now, if the numbers I get indicate that the approximation that I had made is not good approximation, then I'll come back and then use the computer algebra system to solve this equation. So let me just work out the numbers for now. Square root of 2 times the mass, 34 kilogram, times g, 9.8, times the h, that's going to be 1 meter, divided by spring constant, 4750 Newton per meter, all in basic SI units. The answer I get will be in the meters. So I need to convert it to centimeters by multiply by 100 to plug in. So working at the numbers there, I get 0.37 meter or centimeters. Okay. So the number I'm comparing is how does this number compare to 1 meter? And it's a significant fraction of a meter. So the approximation I made, it's probably not good. When I plug in this number, 37.5, it should tell me that that's wrong. Because it will have been, off by more than 1%. So, all right, didn't work. So let me just use computer algebra system and to help me avoid having to do having to use quadratic formula. I mean, I know it's just tedious. So I'm gonna declare all my variables. Okay, and instead of delta x, I'm just gonna use x. I have m, g. I already declared the x. I need the h. I think that's all the variables I need. Using these variables, I'm gonna define my equation. It'll be 1/2 times k times x squared minus m times g times x is equal to, again, two assignment symbols, m times g times h, and I assign this expression into the variable equation. And I use the solve function. You can refer to internal documentation with help solve if you need it. I don't need it. I use this many times. I'm gonna solve for equation, and I'm solving for x. And let me store this into a variable so that I can look at how many solutions I got and make sure I know what I'm gonna work with. So solves. Yeah, I get two solutions because of this square. It kind of doesn't matter if the whole quantity is negative or positive. I'm staring at this. If anything's gonna be negative, I think it's this quantity that will be negative. So let me make sure I stick with the positive answer. So that will be the second answer I got. So solution, the second answer, or the index 1. And let me plug in the numbers. I'll use, this is the solution that I'm gonna work with. And let me substitute in the numbers. Mass is 34 kilogram. K is 4750, and I'm putting these dots to make sure that it does decimal approximation. H is 1 meters, and I think that's everything. Let me see if it'll give me purely numerical answer. Oh, I forgot G, that's why. Okay, G is equal to 9.8. All right, 45.1, or in centimeters, 45.1 centimeter. Yeah, that's definitely quite a bit different from what I had. That's why it wouldn't grade it as correct. Although, you can see that if you are looking for like an approximate answer, like something that's within a factor of 2, then the approximation I made would have been good. Like if you are trying to make sure will the child hit the ground or not, and you add in some engineering safety margin, then then the approximated result could have been good, but not to the 1% tolerance that the system would have been enforcing. You'll need to be able to do this by hand. That's why I keep saying to learn how to do this by hand. But while you're working on homework, let me show you one tool you can use to kind of help you check your answer, to minimize the unnecessary frustration. So this is a free version of what is available on something called Mathematica, or you might have seen it as Wolfram Alpha. So this is a kind of free version of that. It's called the software is called SageMath, and there are different ways of getting at it. This particular website, sagemath.sagemath.org, is the kind of least hassle-some way of getting at it. I also have Sage installed on my computer, which I could have used it to demonstrate, but most people don't have. If you have to install something on your computer, then it becomes very tedious. So let me not do that. So there's a function in Sage called solve. So let me just show you, help solve. So So that's the help file, tells you how to solve. So what I'm going to do is I'm going to use this computer algebra system to just have it solve this system of equations for me. So I read up on the syntax earlier so that I can do this now. Now I need to define the variables. So I think I had the syntax here, var. Okay, that's the. So I need to define my 1, 2, 3, 4, 5, 6 variables. That those are m1, m2, v1, v2, vf1, vf2. Those are vars. Var or vars? I keep forgetting. Var. Okay. M1. I don't know why this is necessary. I don't know Sage all that well. I used Mathematica for a lot longer, so I know Mathematica better, but this is free. Free forever. Okay, so those will define these symbols as variables so that program won't get confused. Now what I need is to specify this solve expression. It kind of works this way. This expression here defines the system of equations you're trying to solve, and these are the variables you're trying to solve for. So let me write it down. Solve. My first equation is the, well, first equation, m1 times v1 plus m2 times v2 is equal to, I need two equal signs. That's, it's an assignment versus a comparison operator. Let me not get into that. m1 times v final 1 plus m2 times v final 2. And that's my first equation. I need my second equation. M1 times V1 squared plus M2 times V2 squared is equal to M1 times V final 1 squared plus M2 times V final 2 squared. All right, that's my system of equations. And I'm wanting to solve it for V final 1 and V final 2. Let's see what it does. Evaluate. And if I were to try to do this by hand, it would have taken me probably 10 minutes, especially if I'm talking. If I'm just writing as quickly as I can, I might do it faster. But if I'm talking, I'm going to take at least 10 minutes. This did a lot more quickly. It took me more time talking. Now, it gives you more than one set of solutions, and the first solution probably has you going, oh, duh. Duh, in the sense of if these two cards kind of just they kind of just missed each other, as in the trailing card just went past the leading card, then all right, that's still an interaction that conserves momentum and energy. So the mathematical solution includes that possibility, which we are going to ignore. We're not looking for that. We did say they collided. So this is the answer that we are looking for. This is the expression for the final velocity of the originally leading card. And yeah, so this complicated expression is, you can do some sanity checks by imagining what the expression would be like if m1 is equal to m2, and I'll leave you up to that. It'll give you some interesting result that's worth thinking through. See if that makes intuitive sense. But in the general case where m1 and m2 are not the same, well, this is the answer to the speed of the leading bumper car. And this is the answer to speed of the trailing bumper car. And this computer algebra system did it a lot faster than I could do it by hand. And this is good for kind of looking up an answer that you can refer to in case you are making some trivial algebra mistakes, and that's preventing you from getting the right answer. So I'm just gonna just not include the signs into my equation. And you will see me start to do that with some of the more formalistic equations. Conservation law equations are first of those equations where you will see me doing that. So I have this, and normally the next 15-20 minutes will be spent going through algebra to solve this all out. Instead of that, I'm going to use the amazing shortcut of computer algebra system. I'm just gonna type in these equations and let the computer algebra system do the solution. Let me make sure all my variables are declared. Okay, and my equation 1 will be the conservation of energy is equal to 1/2 times m1 times v1 squared plus 1/2 times m2 times v2 squared. Okay, and equation 2 will be conservation of momentum m1 times v naught is equal to m1 times v1 plus m2 times v2. Okay, let's make sure I typed those in correctly. And I'm going to have a solve function, solve for a system of equation. That's the system of equation 1 and 2. And I'm going to have it solve for v1 and v2. Me telling the system that also tells it that the other variables may be treated as a known quantities. So, oh, that was quick. Oh, it's solved. So it gives me two solutions, which actually makes sense because I have that squared quantity there. So there should be two set of solutions. And the first solution, if you read through it and think through it carefully, hopefully gives you this sense that, oh, that's the solution you get when these two balls have simply missed each other. The M1 retained its initial speed and M2 continues to not move. So really the solution I want is the second solution. So let me say my solutions are really the previous output, second element. So this is the solution I'm working with. And oh, I don't have to plug in any numbers because it's asking me for symbolic answer. I'm just gonna symbolically type in this. So V1 is gonna be M1 minus, I need the subscript, minus M2 times V naught divided by M1 plus M2. And I think even though this looks a little ugly, it'll be fine. It won't, it'll recognize the correct expression. 2 times M1 times V naught divided by M1 plus M2. Interesting. All right, let's see if they are correct answers. Yep, they are correct. Good. And again, if I'm doing this by hand, it would have taken me another 10, 15 minutes, or maybe 20, I don't know. So yeah, I'm using the shortcut that I'm a little bit um, two-minded. I'm ambivalent about this particular situation. People using computer algebra system, which is because I do think the algebra exercise you get here is good exercise to have. You'll see me do that in lecture, so do that for your own learning. At the same time, if you want to use computer algebra system, take the exact shortcut I've taken now. I think that's totally fine. I don't think other than missing out on a little bit of algebra practice, I don't think you've missed out on anything great and big. So that's my demo of approach that I feel a little bit ambivalent about. But I feel better about this approach than simply looking up equations from the textbook, which it's not cheating, but you learn less from doing that from doing this. Here you enlist to learn how to use the computer algebra system.